So currently facing north, twisting west. Going round now to the south face of the quarry again. It's in shadow, and as we come round, the quarry has got lots of exposure, lots of fluvial deposits with the gravels and the sands. Then if we go around to the east side, and that's just the farmland. Quarry. This is, as you can see, conglomerates and sand, and it belongs to the Chester Formation, which has been called the Kidderminster Formation. Before that it was the Polesworth Formation, but most of you would know it as the Bunter Pebble Beds. It belongs to the Sherwood Sandstone Group. Now these deposits are from the earliest Triassic, and they're deposited in a basin called the Hinckley Basin. We're standing in it. To the west we have a north-south fault-bounded contact with the Carboniferous deposits of the Coventry High. To the east we have a fault with the Younger Mercia mudstone on the downthrown side, and to the southeast we have the Bromsgrove Formation, formerly the Helsby Formation, and that is also a member of the Sherwood Sandstone Group, which is sits above the rocks here. And just to help you visualize that, you may have seen that cross section on the table. We have the Stafford Basin, we have the South Staffs Horst, we have the Knoll Basin, and then we have the Coventry Horst just over here, and we're in the Hinckley Basin, fairly close to this fault. Okay. Get rid of that. Right. A lot of words, you see. Too many for me to remember. Okay, a little bit about the geological setting then. In the early Devonian, we go back a long way now, we were about 30 degrees south. There was a mountain range to the north, which is the Caledonian mountain range, and it was draining south. But by the Westphalian time, the latest part in the Carboniferous, we were at the equator, and it was a flat-lying area with a coal swamp close to sea level with occasional marine incursions. And the deposits of the Carboniferous are on the Coventry Horst, just behind us. At the end of the Carboniferous, beginning of the Permian, we had Pangaea. Now, any geologist here will know Pangaea is where all the continents amassed. So you had continents all the way from near enough the South Pole to the North Pole. Over the South Pole at that time, we had an ice cap had formed at the end of the Carboniferous. And it was big, and sea levels were globally small, very low. And at the end of the Carboniferous, we had the Hercynian mountain building event had finished. The Rheic Ocean had closed, and we had a central Pangaean mountains right down behind us in the south, where Brittany is today. Okay. So the waters from the mountains to the south were now draining northwards into the Midlands, and they deposited things like the Kenilworth sandstone in the early Permian, with its overlying Ashar formation of clays and sands. There was no significant deposits of conglomerates in the Permian as we see here today. During the Permian, the ice cap that developed at the end of the Carboniferous, it started to melt and sea levels rose. We had meandering river systems that fed the Midlands, where we are, with sand and clays. And during the late Permian, the land north of Nottingham, that was flooded by the sea, the Zechstein Sea, where all the carbonates going on deposited and all the evaporites. I'm trying to paint the picture. It wasn't a very high land we were in. During the Permian, we had a series of faults occurred, creating north-south orientated troughs and ridges. And these are a result of Pangaea breaking up. You know, it formed at the end of the Carboniferous. Well, in the Permian it started to break up again in the region of, let's say, the North Atlantic, and the Worcester Basin and this Hinckley Basin were formed at that time. During the early Triassic, when these were deposited, sedimentation rates dramatically increased. The Chester Formation is a consequence of an abrupt development of large-scale, northward flowing, braided river systems. You may have heard of it. It's the Budleigh-Hensis River. This carried millions of tons of debris from the Amorcian Massif in Brittany for up to distances of 400 kilometers. Now that is huge. Okay. Now this persisted up until the latest Anisian period, the Anisian times, which were mid-Triassic. Initially the rivers were depositing the Chester Formation in the restricted basins of the Worcester Basin, but it didn't take long before the rivers were able to inundate the ridges, allowing deposition in adjoining basins, such as the Knoll Basin and now the Hinckley Basin. So what evidence do we have for these rivers? Well, the fossils found in Brittany have been found inside quartzites like these, near Birmingham and in other areas. And this gave the idea that the rivers were transporting coarse clastics all the way from Brittany through the Wessex Basin, up the Worcester Graben and spewing out into the Midlands. So the question is then, what changed to lead to this influx of conglomerates at the start of the Triassic? Why did we not see this in the Permian? After all, the mountains were there. And the research indicates that the answer to this is linked to the end of Permian mass extinction event. So you've probably all heard of that because it was the biggest mass extinction event we've had on the planet. 252 million years ago, there were massive volcanic eruptions over what is now Siberia. And these released huge amounts of greenhouse gases into the atmosphere, and this altered climate patterns. It impacted ecosystems on land and in the sea. And in addition, the eruptions were coming through coal deposits, and this really exacerbated the conditions. This led to global warming, extremes of drought and flood, and acid rain. The rapid change in the climate was significantly greater than we're doing today, much worse. Disastrous consequences, of course, happened for life on Earth. Acid rain was killed off the land vegetation, and it left the mountains susceptible to further erosion. All this increased erosion swamped the ecosystems. We had lethal high temperatures, which probably led to wildfires. We had the ground was eroding fast, and it destroyed the meander systems that existed before the end of Permian mass extinction. In the oceans, you had hypoxia and anoxia, driven by the temperature rise and by the nutrients coming from the land, and the seas also became acidic. So it led to life dying out on a devastating scale. And these greenhouse conditions are believed to have recurred for over 5 million years. So long time. So throughout the early Triassic, this continued, and as did the volcanism going on in Siberia. But by the mid-Triassic, the cessation of the volcanism happened, and that led to climatic stabilization, global recovery of ecosystems, and the re-establishment of meandering rivers. Now, you're probably wondering, why is this guy talking of meandering rivers? Well, these are not meandering rivers. These are different. Okay. So, several models have come up, and there's variances on the models to what has gone on. But there's a general consensus that late Permian tectonics had created a system of troughs and reaches running north-south. Following the end of Permian mass extinction event, we had a huge rise in sedimentation, as we're saying here. BGS advocated that accommodation space was provided by sim rift tectonics, and I might explain that to you later if you don't know. The region was at 15 to 20 degrees north in a hot semi-arid continental setting, and the rivers flowing northwards from the Amorcian Massif were joined by local tributaries adding to the sediment load. Well, what does that mean? It means that not every pebble here has come from Brittany. It has come from other parts, and therefore you should see some diversity in the pebbles. So the depositional setting changed from a fluvial meandering system that happened in the early Permian, the Kenilworth sandstone, meandering rivers, to a braided river system, which we're seeing here today. And then it returned in the mid-Triassic to a meandering river system. Parts of the Sherwood Sandstone group thickened towards the Polesworth Fault. Well, the Polesworth Fault is just about over here on the other side. And that tells us that we're in a half graben. Now, geologists will know what a half graben is. I can tell you again afterwards if you want. Rhythmic and cyclic sedimentation patterns developed as a consequence of many floods followed by many droughts, and this went on and on, and these climatic fluctuations had a major impact. Now, to observe them, what you're supposed to see are rhythms start with hard conglomerates, then they're overlain by sandstones, which are succeeded by mudstones. But I'm going to say now you're not likely to see a full sequence. Upward fining rhythms commonly start with an erosional base, so that's something you can keep your eyes open for when looking in the quarry here. And recognizable bed forms, can we see longitudinal bars which are characteristic of braided river systems? Do we see any cross bedding, any planar bedding? Again, there's geologists here, so when we're looking around, make sure you've got one beside you to explain these things. This is the only good exposure of the Chester Formation in Warwickshire. And we're looking at about 7 to 10 metres in height. And we're seeing pale buff-coloured sandstones overlying well-bedded coarse conglomerates with sandstone lenses. That's what it's telling me here. We'll have to look and take a look. Okay. During the Triassic, now this is key, this was a depicenter. Now, you've all walked up a hill, or you've driven up a hill, to get to this site. And if you go down the bottom, you'll see it's a hill. We're at 85 metres above sea level. And the Coventry Horse over there is about 75 metres above sea level. So we're a little bit higher. We're definitely not a stepicenter. So what's going on? The Roundberry Quarry are hard, in part cemented. They resist weathering. But that's part of the story. At the time these conglomerates were laid down, we were pretty low down in a low-lying area. And it's probable and most likely that during the early Triassic, the boundary fault was active. That's what we mean by syn sedimentary. It was activating, downfaulting as further sediment came into the basin to allow an accumulation. Today the downthrown side is shown on the geological map as being over there to the west. Now that doesn't add up to a deposition taking place here to the east, and I'll explain that. That tells us that we've had, since it was deposited, we've had compression. So if I can show you, you have a fault, you've got deposition taking place, syn sedimentary deposition, so the fault is active throughout the period of deposition, and then at some later stage what we have is compression. And we can see we've had compression because you just have to look at that formation over there and you can see it's dipping. So the compression comes back and the fault is reversed. So instead of being downthrown, it gets pushed back. And the deposits that have been laid down in the basin are pushed up and eroded. So what we can quite safely say is what we're looking at today is only part of what was deposited here originally. And we know that the thickness of the Chester Formation is around about 200 metres in the Hinckley Basin. So, and we're looking at 7 or 10 metres here. So we can tell a lot from that. Underlying the Chester Formation is the Hopworth Breccia. And you probably saw a sample of it on the table. It's not exposed in this quarry, but it is exposed fairly close by. And it's in Stipers Hill Road, actually, on the way to Polesworth. It's a very different breccia and rock than you're seeing here. It's believed, it's composed of a variety of lithologies, and it's interpreted as a scree derived from nearby horsks, reworked by flash floods and deposited in proximal setting to the source. What we're seeing in this quarry is only the Chester Formation. We're going to look at sandstones, which are the yellow things. They're generally poorly cemented, but you might find some that aren't. And we're going to look at the conglomerates, which have a variety of pebbles. They're different colours, and that's because they're different sources. So, I have given you a worksheet. This is it. And your sheet is just literally a series of little checks, little things you can look for when you're looking at the rocks. So, for example, the bed thickness. What is it telling you about water depth? You know, you've got to imagine a bed, a river won't carry rocks, a lot of sediment that's thicker than the depth of the water. And you probably imagine that the river needs to be about 3 times the depth of the thickness of the unit it's depositing. Is there any evidence of cyclicity? Do we see any erosional bases pre-deposition? What about sorting? Is it disorganized or organized? Is there any evidence of coarsening up or any evidence of fining up? It has a lot to do whether it's fluvial or alluvial, apparently. Any evidence of secondary cementation? I do have some acid with me. If anybody wants to test it out, we can play with that. Is there any evidence of draping? Do you recognize cross bedding or planar bedding? Imbrication? Any other sedimentological features? What was the sediment direction of transport? Which way was it flowing? And we should be able to tell that from the patterns we see in the rock. It's supposed to have come from the southwest. I'm going to give you that. That's where it's supposed to come. So if you're finding something else, it could be true, but I'm telling you that's what the experts tell us. Okay. There was a theory that initially that it would have come from the southeast, from other sources, but And if you find something from the southeast, well, we'll take that off too. Okay. What are the conglomerates composed of? Have a look at them. The dominance is quartzite, I will tell you, but there are other lithologies in there. Make a note of the pebble shape. Is it round? Is it spheroid? Is it disc shape? Is the shape related to the lithology? Okay. And what proportion are the shapes? Are they round? Are they proportion more spheroid? Maybe they're just a good mix, a good old jumble. I don't know. But there you are. There's just some tips. So without further ado, I would say we can take a look, unless there's anybody wants to bring anything up before we start.